And it is Monday or Tuesday. I'm not sure. Okay. It's officially Monday class schedule, but it is Tuesday. February 16th, we're in chapter 20, organometallics, the Grignard reactions. Going to make carbon-carbon bonds. Like I said last time, I think this is the heart of the chapter. And like the Diels-Alder reaction, we're making carbon-carbon bonds. So this changes the carbon framework. This is a fundamental transformation. We have homework 5 for chapter 20 due tomorrow, Wednesday. We will be finishing chapter 20 tomorrow. Yes, we have class tomorrow also. Sorry about that. Chapter 21 will start either tomorrow or Friday, depending on time there. And quiz 4 still isn't on Learning Suite. No, it's not on there yet. We'll get it on there later this morning. It'll be due on Thursday, so you have time with the TAs. Today is officially a Monday day, so I don't have office hours. If you do have questions, email me. Zoom in on Thursday. We've got plenty of time to help you with the questions. Regrade requests, a few people did submit regrades. So those are finalized on Wednesday. You just have the 1 week to get those in. I need to see your whole exam and then your specific arguments about that. And I do them all at the same time on Wednesday. So that's coming up too. Questions on anything? All right, the snow's piling up outside, and so are the reactions here inside. Let's see here. We've got a few reactions to jog your memory a little bit. Going back to last time, the 4 on the top there, and I've got kind of a synthesis scheme here. On the bottom, we'll have to fill in the reagents and the reactions there. So let's see, the first one's sodium borohydride with an aldehyde. What will that give? Let's see. Anybody in the class help us out there? Sodium borohydride with an aldehyde. What are we going to get? Remember, it's a reducing agent. So what functional group is the aldehyde going to be converted into? Primary alcohol. Yeah, I think somebody said it. And let's see what it is. There it is. Okay. Primary alcohol after we quench with water. Remember, the hydride comes off here and attacks the positive carbon there, push the electrons up, and then protonate the alcohol. LAH, a little bit different. Remember, the more aggressive reagent, what's that stand for? Lithium aluminum hydride. That's a more diverse reagent that reacts with a number of different functional groups. So with a carboxylic acid, what will it go to here? Also primary alcohol, but it'll add 2 equivalents of the hydride. So it'll give the primary alcohol again. LAH with an ester, or an acid chloride for that matter. What will that give? Kind of the same thing here, right? There you go, another primary alcohol. Now be careful, this next one is the exception to the rule, right? An amide with LAH. Who can help us out with that one? What's the difference there? The amide will go to what? An amine, that's right. So the better leaving group is the aluminum oxide, if you go back through the mechanism there. And it is the primary amine. You add the 2 equivalents. In the intermediate, you lose the aluminum oxide, and then you add the second equivalent of hydride. And we went through that last time. Little review there. Questions on any of those? Did you get 100%? Some people, okay, a little bit. Okay, well, that helps you, remind yourself of that. Let's see. Our reaction scheme here, we've got an alkene with borane. Now, that's different than sodium borohydride. I like to point that out. Borane BH3, that's the neutral thing. What does that do with alkenes? And then after we oxidize with the peroxide, what do we get? Another primary alcohol, right? So I think we got a theme going here. It does the hydroboration there. Primary alcohol with the alkene. Don't forget those reactions. Something like that will be on our final, cumulative final. And then PBr3 with an alcohol. What does that form? Forms the what? the bromide, the primary bromide, without rearrangements. That's an important reaction to form bromides exactly where the alcohol is. The other reagent is thionyl chloride, SOCl2 with alcohols goes to chlorides. PBr3 goes to bromides. So that's an important reaction in conjunction with this one, which is chapter 20 now. So I don't expect you to know too much about these yet. We haven't covered it. But when we react an alkyl halide with magnesium, we're going to get the magnesium bromide. Okay, that's the so-called Grignard reagent. Okay, for Victor Grignard, we'll see him here in a second. Okay, so yeah, this is forming the Grignard reagent with magnesium and any halide, chloride, bromide, not fluoride, but iodide also work well, or chloride. Then we'll react this with a aldehyde and then quench with water. And look what we're going to get. We're going to get the secondary alcohol. 1, 2, 3, 4 carbons from the Grignard, and then 2 carbons from the aldehyde. Okay. So again, it's a similar thing here. Nucleophilic addition, instead of hydride, now it's with a carbon. Now these Grignard reagents are very versatile. A lot of different electrophilic things can be added here, including epoxides. So we can extend that 4-carbon chain by 2 more carbons. And then, yeah, we need to quench with water again. And we'll get the 2-carbon extended, primary alcohol. Here's secondary alcohol from the aldehyde. Okay. And then carbon dioxide. What are we going to get there? Well, that's also a carbonyl group. It's got 2 carbonyls. And after we quench with water, what's it going to be? It's going to be carboxylic acid. Okay. So you see the versatility already of these Grignard reagents. What I like to point out here early on is what we've seen before with alkyl halides or leaving groups with nucleophiles, right? These are what? Partially positive carbons. They're electrophilic. They'll react with nucleophiles. And we know that reaction to give the cyanide here. That's from 352. But now look, when we convert it to the Grignard reagent, we form a metal carbon bond. What's more electronegative now? The carbon, right? Metals are 1, 1.5 on the Pauling scale. They're on the left side of the periodic table. Carbon is more electronegative now. So the bond here is actually toward carbon, and that's the partially negative end now, the carbon. So you see it acts as a nucleophile with these electrophilic groups. So we switched the polarity, you can say, of this halide. Initially it was what, electrophilic, reacting with nucleophiles. Okay. These reagents, cyanides, everything we learned, SN2, those type of reactions. But now if we convert it with the magnesium, look, it's now the nucleophile, and it reacts with a bunch of what? Electrophiles. Okay. So that concept, I think, is good to point out right at the first. So when we start piling up all these new reactions, going through this Grignard stuff, you've got a way to keep it straight, okay? Here, initially, with a leaving group, right? This is pulling on those electrons, partially positive there. But now we did a switcheroo. Magnesium inserted between the carbon and the bromide bond. We'll look at that in detail. That makes a metal carbon bond, which is now the nucleophile reacting with electrophilic reagents. Okay, so those designations mechanistically, hopefully, will help us keep track of those things. All right, let's get into the details of these organometallic reactions and what we need to know there. We're going to go through a few different ones today. We're going to look at alkyl lithiums, okay? And these lithium reagents are very reactive. They're very basic, okay? And the lithium's, on the far left side of the periodic table, right? So it's very electropositive, which makes this equivalent, you could say, of this. The carbon is a carbanion, and the metal is a positive ion. Now, in solution, when we form them, they're not actually salts. They can be dissolved in organic solutions, but we think of them this way, and there's our nucleophile, right? That's what we're talking about. So the lithiums are fine. They'll react in a lot of ways, just like the Grignard reagents. However, they tend to be basic, and some other things can often go on, acid-base chemistry. The more versatile ones are the alkyl magnesium halides. Okay, these are the Grignard reagents. Magnesium's alkaline earth metal. It's in the second row, so it can be in what? The +2 oxidation state. And you see it has two anions on it, the carbanion and the halide anion, right? So magnesium is formally in the +2 oxidation state. Now, it's not a true salt, okay? It will be in solution, but that's how we'll look at it. These are the really good nucleophiles that you just saw there. They're less basic than the lithiums, so they tend to be a little more versatile. We also have these. These are the cuprates, okay? And these organocuprates, copper's on the far right side of the transition metal block, right? Element 29 there. So it's not as electropositive. And you've got three things here on a copper. It's going to react in a less aggressive way than the magnesium, or certainly the lithiums. And it's going to be specific for enones. So we'll kind of limit the reagents it works with. The most versatile one are the Grignard reagents. Quick thing on names here, we call them alkyl metals. Okay, so methyl lithium, for example. Okay, how about this one? Ethenyl lithium, alkyl, the prefix name. There are vinyl lithium. You could call that vinyl lithium. Magnesium. Well, let's do a specific one. So how do we name the Grignard reagents? That's probably the important one to name. So this specific one would be ethyl, magnesium, bromide. So whatever halide's on there, you see you got two things on the magnesium, ethyl, an alkyl group, magnesium, bromide. I think that's all we need to do on the names there. All right, a little bit on the preparation of how these guys are made. And this reaction actually is quite complicated, and there's still some controversy about the actual mechanisms. They do vary depending on the metal or the alkyl halide you're using, but we'll go through this. Okay, you can take an alkyl halide plus two equivalents of lithium metal. Now that's the shiny stuff. That's not the salt. That's the reduced form of the metal. And those first row metals are very reactive, right? Very pyrophoric. You have to keep them away from air and water and very carefully add them. But to form the alkyl lithium, we need two equivalents here. And one lithium will end up on the butyl, and another lithium will end up on the bromide. And this is a salt now. The byproduct is a salt that will precipitate out. A lot of times we do it in a hydrocarbon solvent like hexanes or THF, some non-protic solvent. We can't have any OH groups or acid available because these are very basic. They'll react very quickly. If we have any water in there, okay, it'll go right away to butane, okay, plus lithium hydroxide, okay? I think you can see why, right? This is very basic. Grab the proton, you'll have hydroxide, lithium hydroxide in that. Sometimes we use this as a mechanistic marker. We'll use heavy water, the isotope here, and we'll put that isotope right where the halide was, okay? And we can kind of tell mechanistically where things end up there, but yeah. The actual reaction here of how this forms, this is in the zero oxidation state. That's the reduced shiny metal. And now what? Lithium is in the +1 oxidation state. And we think of that as a carbanion, right? It's the more electronegative part on the metal. So I think that's good there. Let's look at the Grignard reagents. And all of these can be sp3 or sp2, primary, secondary, tertiary, which is great because they're very versatile, okay? The halide can be almost anything, okay? As long as there's no alcohols or OH groups or groups that are slightly acidic within the molecule. Now, a Grignard reagent, let's look at a different one here. How about cyclohexylchloride plus magnesium metal? And again, that's the reduced stuff, the shiny stuff, okay? And we just react this in an inert solvent. A lot of times we use that cyclic ether, it's called THF, for tetrahydrofuran. The oxygen has 2 lone pairs that can be Lewis, basic, that can stabilize the metal, but there's no proton here. There's no OH group, okay? Nothing acidic. So it's an inert solvent that just helps stabilize the reaction. And what do we get? We get the cyclohexyl magnesium chloride in this case. Yep, okay. And yeah, magnesium is now in the +2 oxidation state. It's got 2 bonds to 2 other more electronegative atoms. And we can see here, this can function as a nucleophile now, right? And that's what we're going to be doing with that. Well, how does the THF or ether, diethyl ether is also sometimes used. You can see the ether oxygen would help stabilize the positive metal and help keep it in solution, okay? But again, we got to keep it away from water. If any water gets in there, or alcohol or acetic acid or anything, what can occur here? Just grab a proton and we're back to hexanes, okay? We don't want that. We want to add normally another electrophile to make a more useful bond there. Okay, cuprates, kind of in the similar way. Yeah, let me do a little bit more on cuprates maybe. So we got the lithiums, the Grignards, and the cuprates. We have to take an alkyl iodide or lithium, an alkyl lithium with a copper 1 halide, iodide in this case. And you see this is going to add to our copper, okay? And it forms an alkyl copper plus a lithium iodide. Now that's a copper 1 species, you see. It hasn't really changed its oxidation state at all. And lithium hasn't either. It's done what's called a metal halogen exchange. But if we have another equivalent of the lithium, you see, then we can add here, and we get the second one on there. And now this copper is negatively charged, and it has the lithium associated with it. Yeah, I'm sorry, up above there I wrote copper with an X. It's copper with another metal there. So this is the cuprate right here. Okay, and this is the thing that's going to add to enones, and we'll see that later on. But again, it's a metal carbon bond. Okay, it is nucleophilic, but it's not as reactive as that. All right, let's get into the reactions now with the Grignard reagents. These are the important ones. And forming carbon-carbon bonds is synthetically probably the most important part about organic synthesis. And why do we say that? CC bonds. And, you know, you're going to see a lot of reactions with this. You're going to think, well, big deal, it's just another reaction we're learning. Well, all the other reactions we've really learned up this far, stuff the Diels-Alder, that form carbon-carbon bonds. And I guess putting a cyanide on, SN2 chemistry-wise, forming a carbon-carbon bond also. But the Grignards are so versatile with so many different electrophiles. It's going to give a variety of carbon frameworks or skeletal, you could say. And it's changing that skeletal framework of the molecule that's really fundamental, okay? And Grignards do this in a very unique way. So here we've got our Grignard, okay? And what are we going to do? Well, let's show how we make it, first of all. We're making a specific one. We've got magnesium. And if you leave out the THF or the ether, that's fine. Just make sure you don't put ethanol, methanol, or acetic acid here, okay? You need the halide and then the reduced metal, and you can form the Grignard, okay? So this Grignard reagent now is going to react with the electrophiles. And we're going to do a variety of them. Let's do the first one here just with this aldehyde. That has a name, that's formaldehyde. We'll have a later chapter where we do the naming of aldehydes and ketones. But with this one here, what are we going to do? Well, we're going to add our Grignard reagent, okay? That's got the carbonyl there, formaldehyde. And what are we going to get? Well, we'll get this. And it's good to keep track, you know, of the hydrogens here, of the framework, whatever. And now the second step, quenching with water. Or dilute HCl, okay? It's just enough protic strength to what? Protonate the alkoxide. Because that's what we get. We've got O minus here. What happened to the magnesium? Well, it's there. It's the salt. It's the magnesium bromide salt of the alkoxide at first. Do you see the flow of electrons where everything ends up so far? Okay. And then what does the protonation thing here do? It gives us what? Primary alcohol. Oh, okay, big deal. You see this carbon right here came from the formaldehyde. And it's this bond right here that we just made, okay? So kind of look at it backwards and forwards. Okay, that's not the only aldehyde though, of course. How about if we have this aldehyde? The 3-carbon aldehyde. Well, let's do the same thing. All right, that's where we're gonna add. So what are we gonna have? We're gonna have this. It brought in 3 carbons there and 2 carbons here from the Grignard. The molecule looks symmetric now. You can't really tell which end came in how. And then quench with same thing here. Dilute acid or water. And what do we get? Oh, we get the secondary alcohol. Okay. Let's see. That's pretty good, isn't it? We can make any kind of primary alcohol. We can make any kind of a secondary alcohol. Okay. Well, Victor Grignard said, well, can I make tertiary alcohols? What do we need to react now to get a tertiary alcohol instead? So what's the next reaction here? Formaldehyde, aldehyde. What do we need here to get a tertiary alcohol now? Ketone, very good. Simple one, let's just use acetone. Ketone now, same idea, right? We're just flowing electrons the same way, but we're varying the electrophile, right? Different carbonyl group. So what are we going to get? That ethyl group on there. O minus right now. Okay. 1, 2, 3. Counting carbons is probably your most important task once you get the mechanism down. And then quench with water. What are we going to get? Ah, yeah. Tertiary alcohol. Okay. How about some aromatic ones? Let's do some other variations here. How about, let's see if this holds up with some other substrates, huh? We'll stick with ethyl maybe. Oh, no, let's branch out here. How about vinyl? Vinyl bromide, magnesium. And then we're going to react it with benzaldehyde. Okay. And we're going to react it with this ketone. So a little more complicated, right? What's our Grignard reagent? It's going to be the vinyl mag bromide. And then with benzaldehyde, going to react on the carbonyl here. And then quench. We'll just say quench with water. We'll skip that step. And look, the benzene's there. Here's our bond we just made. And we made that, secondary alcohol from an aldehyde. So you can always check that. Formaldehyde always gives what? Primary alcohols. Aldehydes always give secondary alcohols. Ketones, which we got coming up, always give what? Tertiary alcohol. You can kind of see that. Let's go ahead and do this one. Separate reaction. What are we going to get? There's the vinyl group. There's where the ketone was. And then we got to add this allyl piece on the 1, 2, 4, 5 carbons. Yep, 1, 2, 3, 4, 5. Yeah. Tertiary alcohol. Okay. So we've got a feel for it going in the forward direction there. Okay. Let's look at esters. How about if we have a little more complicated substrate now? Here's our ethyl one, and let's use this ester here. Now that's a carbonyl, right? So we're going to have to figure this out, and we're actually going to use 2 equivalents here of our Grignard reagent. And that's the difference now. We've got an intermediate. And let's see, let me give you the product, and then we'll figure out how this came about. Oh, let's make this a little bit different. Let's put a benzene over here. Yeah. Okay, esters. What type of alcohol is it? It's tertiary. You can see the benzene and then that methylene right here. Oh, and that must have been where the carbonyl was. And then you see the 2 ethyls here. So we made 2 bonds at the same time. So we're going to have to modify our mechanism, but not much, right? Because this is a carbonyl. So let's just start out how we know here. And I like this because, you know, we can figure out some of these mechanisms just by thinking about, you know, what's on there and following what we know how to do to begin with. Okay, so there's 1 ethyl on there. We have this methoxy, though, from the ester, right? What do I need to do now? What's my next step? Bring the electrons back out, because this is what? We'd call this a leaving group, right? This could come off under these basic conditions. We have these strong anionic conditions from the Grignard reagent. So let's just do that. That's our tetrahedral intermediate we talked about last time, right? So here's our potential leaving group. And it's not in the product. So let's have it pop off. And what do we get? We get a ketone. Are ketones reactive with Grignard reagents? Yeah, they sure are. We just did one, right? And what do Grignard reactions with ketones always give? They always give tertiary alcohol products. And you can see from the structure, right? So we got to add another ethyl mag bromide here. Let's go ahead and do that. And yeah, we can't really see this yet, but yeah, let's get that second one on there. There it is. O minus. That would be after the second addition. And yeah, just quench with water. Yeah, well, that would do it. Okay. So yeah, the first one adds, we get the tetrahedral intermediate. It's got a potential leaving group. Where does this ONE end up? Well, it ends up right here on a salt, methoxy magnesium bromide. It's a byproduct. When we quench with water at the end here, you see we'll get what? Some methanol. Okay, so it's not forgotten. But it's so water soluble, a lot of times it'll just wash out. So we won't need to worry about it. The main thing we're interested in is this with the 2 additions here. Okay. Now I think you can see that same thing with if you had a chloride. Okay. So esters And acid chlorides react the same way. There we'd even have a better leaving group. We'd have the chloride right here, okay? So, notice these are derivatives of carboxylic acids where they still have the carbonyl, but they also have a leaving group. So they will take two equivalents. You should show that. And we'll put that on the quiz or a test, right? So you'll see it's extra equivalent. The others all added just one equivalent, okay? Let's see if we can do another one here. And we're going to do it in the opposite direction. Let's see. How about if we want to form this product? Oops. Alcohol with two vinyl groups on here now. Okay, so it's a tertiary alcohol. You see two of the groups are the same. It's really difficult to add two different Grignard reagents because they're so reactive and the ketone intermediate comes out very quickly. So for these additions to esters and acid chlorides, you always see two of the same groups here. Okay. So what did this come from? Well, it must have been what? Grignard reagent. It must have been the vinyl magnesium bromide or chloride. And then what substrate? You can't really tell whether it was an ester or an acid chloride, but it had to have the isopropyl, a carbonyl, and let's say the acid chloride, and quench with water. I should say a 2 out here in front of that. Does that give that product? I think so. All right, now let's propose something. Let's propose a synthesis of a little bit different product here and see what are the different ways we could make it. And I always like to see, what people in the class say about this. How could you make this alcohol? Let's say you got a job at some chemical company and your boss comes to you, hey, we need 10 kilos of that next Friday. We got a customer. Your job's to go in the lab and make that 10 kilos. That's a lot. So you better come up with a good route. Okay. So, how would you make that? First of all, what type of alcohol is it? It's tertiary. It's got a vinyl, a methyl, and a phenyl group on it. You can start with anything. Okay, but you remember back, oh yeah, Dr. Andrus babbled on and on about that Grignard reaction. That made a lot of alcohols. Maybe I ought to do a Grignard. Okay, so use a Grignard reaction, but think about that for a minute. How are you going to do that? Well, which bond here is strategic? You're going to have to plan, right? Well, all those bonds I just marked there could be made with Grignard reactions, right? So let's see. Maybe let's take, which one? Which Grignard do you want to use? So we would use what, a phenyl Grignard with the benzene on the halide of benzene, or a vinyl Grignard, or a methyl Grignard? Which one do you want to do first? Take your pick. Phenyl, okay. So if we do phenyl Grignard, then that's going to kind of dictate what our electrophile is going to be, right? Okay, so we look this up and, oh yeah, we can do that on large scale. Make a lot of that. Phenyl magnesium chloride. And then to get to the product right there, what electrophile do we need? Now it's a tertiary alcohol. So what do we need? An aldehyde, a ketone, formaldehyde, an epoxide. What do we need? We need a ketone. And that ketone has to have the other two groups on it, right? So we better have this ketone. Okay? And that would work. Okay? That's only one way. The Grignard is versatile. How else could we do it? How about if we had the methyl, mag bromide, or chloride, whatever? Then which would we need here? We'd have to have the vinyl and the ketone and the benzene on there. Is that, oh, there's one more, right? What's the other one? We have the vinyl, right? Okay. And this is kind of tedious, I'd say, but it's going to point out something important here, I think, in the end. All three of those work. Which one do you think is the cheapest? Which way is your company going to make more money? Let's see. All these Grignards are available. What about these electrophiles? Which electrophile looks cheapest? In fact, you know how to make a couple of these electrophiles, I think. Do you know how to make that electrophile? In fact, there's a name for that one, right? That's acetophenone, okay? You'd make that with your old friend, Friedel-Crafts acylation. So that way you might be able to do two cheap reactions. And the vinyl bromide is also available. You'd have to look at the halides and where those come from. But that one is probably the most cost-effective way. This electrophile, vinyl phenyl ketone, that one's a little pricier. You might have to do an oxidation of the alcohol, and you might actually have to do another Grignard to get a hold of that one. So that would be what, PCC? And then this one here, you'd have to start with this and do a reaction with what? Benzaldehyde, okay? Whereas this one here, I think you could just do the vinyl Grignard and then add to acetophenone. Anyway, there'd be ways to analyze this, which would be the best one. This one's not bad either. This vinyl methyl ketone, MVK, that's not too expensive either, but I think this is the route I saw in the literature that was pretty well known. Anyway, just give you a little experience with thinking about the Grignard and how it might be used in a little more difficult way there. All right, let's look at one more here with the acid chloride. The acid chloride, a little bit different this time. And let's add 2 phenyl magnesium chlorides to it. Provide the product after quenching. So yeah, notice we sometimes switch on you which substrate we draw over the arrow. Don't let that throw you off. Our nucleophile is the phenyl Grignard. And you can think about it stepwise, right? The first intermediate would look like this. That's after one going on and losing the chloride coming off, right? And then what would be the true product here after quenching? Tertiary alcohol, right? 2 benzenes on there. Okay, did you get that product? Okay, getting a little better at it maybe. All right, speaking of acid chlorides, if we use instead the dialkyl copper lithium, we call it a cuprate. So this means 2 ethyl groups on the copper with that lithium thing here. These react with carbonyls with acid chlorides, but they don't have enough power to react with simple ketones. So it will add once, and if we wanted it to just add the once, we'd use the cuprate, and that would be our product. So I think you can go through that intermediate we've done before, right? With the ethyl group on there. And after one alkyl group comes off the cuprate, and it can only transfer one of these, okay? And the byproduct here is ethyl copper. And again, that's a late transition metal, so it's not nearly as reactive as the magnesiums or the lithium. So we'll stop there. Tetrahedral intermediate will just collapse and give the ketone product, okay? We'll get back to cuprates in a second with enones. What I want to do now is some more electrophiles with the Grignard reagents. Okay. I warned you about this. Yeah, they are quite versatile. So let's see what we're going to have here. Here's phenyl magnesium bromide. We'd get that from bromobenzene, and we know how to brominate benzene. So you can see we could go all the way back to this, right? And what would we do? We'd have the bromine, iron, right? That'd be step 1. And then what would be step 2 here? The magnesium. So I like to kind of point things out how they might be used in a sequence here. So if we get this now, and then we quench with, or react with carbon dioxide, and then dilute HCl, we're going to get the benzene with a carboxylic acid on there. Remember the name of that? Benzoic acid. Okay, how does this work? Let's see. Mechanistically, the nucleophile is the Grignard. The electrophile now is not an aldehyde or a ketone or an acid chloride or ester. What's our electrophile? CO2? Carbon dioxide? What is CO2? Well, it's carbon with two carbonyls. Has a carbonyl, has two of them, right? So what can we do here mechanistically? Let's go ahead and do it. Yeah, okay. That central carbon of CO2. And that's just dry ice. You've played around with dry ice before. In the lab, we just crush it up and dump it in to a flask with a nucleophile in it and let it warm up. A lot of times we cool it down at first. But the CO2 can be handled quite easily there, dry ice. And so let's add here. And what do we get? We get O minus. Oh, it looks pretty straightforward, right? It's not too bad. And so what's the dilute HCl in there for? Well, at first, this is the magnesium bromide carboxylate salt. We need to what? Lower the pH below what? The pH has to be below 5. Remember the pKa of benzoic acid, 4.7 to be exact. So if you have dilute HCl, you go down to pH of 2 or 3, whatever. At that point, what? We can protonate the carboxylate and keep that protonated. If we go above pH 5, just neutral water or basic solution, it will be still this, okay, the carboxylate. But if we want the neutral carboxylic acid, we have to acidify there. Questions on that? Can make any carboxylic acid from any Grignard reagent that way. All right, another reaction that's very versatile are the epoxides. We've already seen a little bit about that. Let's go back to this one we looked at, ethyl with ethylene oxide, quench with water, and what are we going to get? Now the aldehyde and ketone reactions, it just involved one carbon in the electrophile. Now there's really two carbons involved here in our electrophile, right? And we're going to add this here. Wait a minute, this is an ether, right? We use THF or diethyl ether as a solvent. And I said those were inert, they didn't react. Why is this ether now reacting the epoxide? Let's see if we can remember that concept. We've used epoxides before with the nucleophiles in 351. Why are we able to react this ether where THF and diethyl ether don't react? What's the main idea here now? Two partially positive carbons, yeah. Okay, I like that. What else about this? The bond angles here. Yeah, you've got angle strain here, which is really a major issue. This is sp3 hybridized. It wants to be 109.5. But in a three-membered ring, this bond angle right here is constrained to be what, 60? Oh, that's not happy. It wants to relieve that. And when we attack the epoxide, we're going to relieve that angle strain. And you're right, you've got those more electropositive carbons there. But we have two in a open ether too, or a five-membered ether. So this one's a little special where the ring strain, I think, the major issue. So what do we get here? We're going to pop that open and get what? This bond to form right there. And notice we have two new carbons now added where the electrophile was. Whereas before the aldehyde ketone, we just had the one carbon right where the carbonyl was. Okay. We push this open and then quench with water. What do we get? The alcohol product. Okay. That's good. What about this one? We got the same epoxide. Now we have gem dimethyl on this side, quaternary carbon. here we have a primary carbon, hydroxide. Which end is going to open up? Are we going to attack the nucleophile here on the left, or attack the nucleophile here on the right? Maybe we can poll the class. We've got enough people here. And how many say we're going to attack here on the left? Okay, yeah, most people. Anybody want to argue for the one on the right? Okay, one there. What type of nucleophile is this? Is it charged or neutral? Remember, that was the issue when we looked at this regioselective opening of epoxides before in 351. If we were under SN1 type conditions where this was ionizing under acidic conditions, we would attack over here because that'd be a tertiary carbocation opening up the epoxide. But here, what type of nucleophile do we have with a Grignard? It's what? You can think of it as charged, okay? So that's a strong nucleophile, right? Where's a strong nucleophile going to want to attack? At a primary or secondary position, right? That's SN2 type chemistry. So let's go ahead and do that. Yep. Let's attack there. And you can see this is a bimolecular reaction, so it'd be slower over here, right? Because that would be a more hindered position. So if we attack at the primary spot, pop that open, get that bond there. And yeah, we get O minus right there. So we just made this bond. You know, when you go through your notes, kind of keep track of the bonds, you know, the strategic positions where things have changed. Carbon-carbon bonds, that's what we've been doing the whole time today, right? And then what do we do here? Let's quench with acid or water, whatever. And we get this alcohol as our product. Not one. We add it over here. What would that give us? It'd give us phenyl right next to those gem dimethyls, right? And then that primary. Okay. These are constitutional isomers, right? Different order. Because not attacking here, because that's a more hindered spot. We want to attack at this primary spot here and then pop it up. Okay. So given the choice, go with the SN2 type reactivity with a Grignard. All right, we do have a minute here. We can finish the last one. And next time we'll be doing a lot of synthetic applications of these organometallics and combining them with some other reactions just like we did here. How about an unsaturated ketone? Okay, now, if I react this with lithium, methyl lithium, or methyl magnesium bromide, quench with water, we're going to get what product? Well, there's our carbonyl. We just attack it. Okay. And that's fine. That's what the product will be. With either one, the Grignards or the lithiums, we'll add at that carbonyl position. I get this. If we react with the methyl cuprate, and that looks kind of funny, doesn't it? Two methyls on a copper and then a lithium. There's actually a lithium salt. There's actually a negative charge on the copper. You can draw it out here and see what it looks like. It's got extra d electrons on it. Okay, that's funny looking, right? It's going to react differently, okay? In fact, after we quench here with water, it's going to be this. The ketone's still there? Wait a minute, what happened here? The methyl group got added, but it added to this position here, the beta position, not at the carbonyl position. So what's going on here? Now, I told you the coppers are less reactive. It's a different reactivity. So let's react here instead. Okay? And that's that beta position. And you'll see why in a second when we examine the intermediate. You know, you could say, well, conceptually it's nucleophilic. Why doesn't it add there? It could, you know, and these reagents certainly do that. They're more reactive. But the cuprate adds at that beta position, and it gives this. We call that the enolate. Put the methyl nucleophile, the beta position, we have to push these electrons up here between the alpha and the carbonyl position, right? and then the negative charge up on oxygen, which is where it wants to be, right? We get that same thing here, but look, we get a resonance stabilized now, O minus, okay? What's the resonance stabilization? Well, it's this. And that's what cuprates need. They need a more stable intermediate in order to add at all, okay? They don't add on their own to ketones or aldehydes. They'll add to acid chlorides and give a ketone. But cuprates have to have this extra stabilization in order to add at all, okay? So you see this O minus here can resonate in those two spots. So the addition of this late transition metal organometallic adds at this beta position to benefit from the stabilization of that pathway. Then how do we get to this product here? Well, just protonate either one, or push the electrons here and protonate with the acid over there. And it does get back the carbonyl. The carbon-oxygen pi bond is more stable than just protonating here. Okay, we could protonate up there, and we'd get what's called an enol. An enol would tautomerize very quickly to the ketone version. Okay, we'll say more about that later. Maybe we mentioned tautomerization before in 351, or you saw that before. But yeah, that's the story with the cuprates. But yeah, we've done a lot today, guys. Reactions are piling up in here. But I've given you a way to deal with it, I think. Focus on the electrophile, nucleophile, and the intermediate, and what it looks like mechanistically, and we'll keep track of it. We'll review that and do synthesis stuff next time. Very good. Thank you.